Chapter 13, Newton's Law of Gravity. Every mass in the universe has a gravitational attraction to every other mass in the universe. So any mass that you have in the universe is attracted to any other mass in the universe, and it's related by Newton's Law of Gravity. The force of gravity is equal to negative some constant g, which is the gravitational constant, mass 1 times mass 2, over the distance between them squared. And when we talk about the distance between two masses, we go from the center of mass 1 to the center of mass 2, wherever that may be. So you always go from the center of mass to center of mass. You do not necessarily go, if mass 1 were spherical and mass 2 were spherical, from the surface to the surface. You go from the center of mass to the center of mass. Forces equal and opposite, so these two masses are attracted to one another by equal forces. And this g is the universal gravitational constant. It has a value of 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. So it just kind of rolls off the tongue. It's a easy to remember constant. 6.67 times 10 to the minus 11. It is the gravitational constant. And the negative sign means this is an attractive force between masses. Here are some beautiful features of this gravity law. The gravitational force acts from a distance between two particles regardless of the medium that separates them. For instance, we're going to be talking about the sun here in a moment. And if we had the sun and the earth is attracted to the sun, and that force is between them at a distance, regardless if something that passes in between. If the moon were to pass in between the earth and the sun, they still would have that same gravitational force between the earth and the sun, regardless of the fact that the moon has passed in between, say in a solar eclipse or something like that. So the earth doesn't go flying off into space as a result. The force decreases rapidly with increasing separation and falls off as the distance squared. Every mass has a gravitational attraction to every other mass. You have a gravitational attraction to the distant galaxy Andromeda. It is 2.9 million light years away, but there is a force between you and the galaxy. It's not very big because 2.9 million light years is a very far distance. As you go 1 over that distance squared, it makes that force pretty minute. It does exist, but it's pretty insignificant. The gravitational force is proportional to the mass of each particle. If I'm talking about the force between, say, me and the Earth, the distance between us is actually between my center of mass and the Earth's center of mass, which would be the radius of the Earth. And even though the Earth is so massive, and this force is proportional to that, that force ultimately is just about 170 pounds. So I have 170 pounds of gravitational attraction between me and the Earth at a distance of the Earth's radius. And the gravitational force of a uniform spherical mass distribution on a particle outside the sphere is the same as if the entire sphere were concentrated at its center. So if I'm talking about the gravitational attraction between a sphere and something else, I treat the sphere as if all of its mass were located at its center of mass, which is in the center of the sphere. I don't go from the surface to that object. I go from the center, where the center of mass is, to wherever that object is. Let's try an example of this gravitational force. What is the force of attraction between Ben, 75 kilograms, and Jen, 55 kilograms, if they are 1 meter apart? So here's Ben, and here's Jen. I guess Jennifer Lopez. They're still dating, right? Ben Affleck and Jennifer Lopez. Are they still dating? Maybe I need to update my PowerPoints. So we have Ben and we have Jen. Let's go and update it. Yeah, Ben and Jennifer Garner. All right, so they are together. And if they were 1 meter apart, what would be the force of attraction between them? Well, the magnitude of that force would be G mass 1, mass 2 over their distance squared. G is 6.67 times 10 to the minus 11. Ben is 75 kilograms. Jen is 55 kilograms. And they're 1 meter apart. This is a force of 2.75 times 10 to the minus 7 newtons. 2.75 times 10 to the minus 7 newtons. Not enough for them to spontaneously collide, because there's other forces involved, like air friction, friction on the ground, that might prevent this really small force from being overwhelming and taking place. But there is a force. For a freely falling object of mass m near the Earth's surface, we get that your weight, or this mass, the weight of this mass, mg, is equal to the force of attraction between the Earth and the mass, which would be g, mass of the Earth, mass of the object, over the distance between the object, which is the radius of the Earth, squared. So if you're anywhere near the surface of the Earth, your weight, which is mass times g, the little g that we know and love, 9.80 meters per second squared, that weight is really due to the gravitational attractive force between you and the Earth at a distance of the Earth's radius. Note that if I cancel out the mass here, I get a value for this little g that we know and love. Little g is 9.80 meters per second squared. It's actually based on physical phenomena like the gravitational constant, the mass of the Earth, and the radius of the Earth squared. So, if I knew what those were, I could actually calculate what the gravitational acceleration should be at the surface of the Earth. And indeed, if you put in g 6.67 times 10 to the minus 11, the mass of the Earth 6 times 10 to the 24 kilograms, and the radius of the Earth 6.37 times 10 to the 6 meters, square that, you get 9.80 meters per second squared. The gravitational acceleration on the moon is 1/6 that of the Earth. So if you went to the moon, you would only feel like you weighed 1/6 as much, because the gravitational acceleration is 1/6 as much. Your mass is the same, but your acceleration would be only 1/6 as much. The moon is much smaller than the Earth. It's got a whole lot less mass, I think about 1/80th the mass, but you're closer to the moon as far as your distance from the mass, because the moon's radius is smaller. So there are mitigating things going on here that ultimately set up the acceleration to be 1/6 that of the Earth. So if you weighed 180 pounds on the Earth, you would only weigh 30 pounds on the moon. That means in the future, if you were to take a weekend vacation, one of the best things you could do would be to jump into a spacecraft, travel to the moon, and play basketball all weekend. Because all of a sudden you have Earth muscles, which are designed for a 180-pound person, and you're working under a 30-pound gravity, so you'll be able to jump all over the place, dunk the ball, play basketball all weekend, not hurt your knees when you fall, and it'll be a great experience. And then come back before Monday morning so you can go back to work. You don't want to stay too long on the moon, because if you do, then your muscles will start to atrophy and you'll become a moon person, and then it won't be such a great experience to play basketball. But visit the moon. So you still have the same mass, but since the acceleration of gravity is different, you have a different weight on the moon. Using the fact that the radius of the Earth is 6.37 times 10 to the 6 meters, we can find the mass and density of the Earth based on this gravitational force and this definition of acceleration. Reverse engineering, the mass of the Earth is equal to the gravitational acceleration, little g, 9.8, times the radius of the Earth squared over the gravitational constant. This would be 9.8 times 6.4 times 10 to the 6 meters, square that, over 6.67 times 10 to the minus 11, and we get that the mass of the Earth is 6 times 10 to the 24 kilograms. How about that? If you took note in our very first chapter in the first lecture, I described a method that you could go to the beach, and if you were at the beach and you were tired of throwing the frisbee around or throwing the football around or going swimming, then maybe you might want to take a break and calculate the radius of the Earth. Something you can do at the beach, because if you watch a sunset and you watch a sunset go below the horizon, you can suddenly stand up and then you would still see the sun above the horizon from your new perspective. Count how many seconds it took for the sun to set again, which would be approximately 10 seconds. And based on how far the Earth rotates in 10 seconds, you can calculate, due to geometry, what the radius of the Earth is. So by staying in one place on the Earth, you can calculate the radius of the Earth. If you further did other experiments at the beach and you dropped a few things, calculate the acceleration of gravity, you could then calculate the mass of the Earth. How cool is that? So you could stay in one place on the Earth and do a few simple experiments that you could do with just stuff laying around, and you can calculate the mass of the Earth. Pretty cool. You could also calculate the density of the Earth. It's the mass of the Earth divided by its volume. Treat the Earth as a sphere, 4/3 pi r cubed. And if I put in those numbers, the density of the Earth on the average is 5.5 times 10 to the 3 kilograms per meter cube, which is, since by definition pure water is 1,000 kilograms per meter cube, this is 5.5 times the density of water. That's the average density of the Earth. You could do that at the beach as well. So this is really fun. These are fun physics problems because they allow you to understand something about your world and that you can do just simply by just staying in one spot. How about that? Kepler's laws. In early times, before the internet, before TV, before cable, before there was entertainment every night of the week, one of the best things you would do if you were an ancient astronomer or just an ancient person is to walk outside and look up at the sky. Entertaining enough. And there was no light pollution, so you would see all the 6,000 stars that you possibly can see with the naked eye on any given night. It would be a beautiful sight, and you would watch what was happening up there. You would recognize certain constellations, and you would know a lot about the sky, and you would see some unusual things going on with the sky as a function of time. You would see basically that the sky would rise in the east and set in the west on any particular night, and everything would seem to move together. But over the course of days and weeks, you would see some very bright objects, brighter than the other stars, and these bright objects would tend to make their way in the opposite direction across the sky. So they too would move with the sky on any given night. Over the course of days, weeks, and months, they would find their way to wander across in the opposite direction. And we call these wanderers planets. So the planets would wander in the opposite direction, and every once in a while these planets would do a loop-de-loop in the sky. They would wander back this way, and then they'd kind of come back the way they were coming from, and loop around, and then continue on their way. And these ancient astronomers were trying to figure out what was going on with these wandering bright objects. Well, here's one explanation. And Ptolemy, in 100 to 170 AD, had a view of the universe where the Earth was at the center, a geocentric model, and that the planets would go around the Earth over a main path called a deferent. And every once in a while, they would hit another extra circle called an epicycle, which would help explain this backward motion, this loop-to-loop motion that the planets would sometimes go through. So as the planets were going around this deferent, right before they became their brightest in the sky, they would do this loop-back behavior, which was explained by this epicycle, and then they would continue on their way. But if you were a good astronomer, you would find that to really explain all the positions of the planets, you need more than one epicycle. You would need an epicycle upon an epicycle upon an epicycle. There would be many epicycles to try to explain the exact position of the planets. It became quite complicated. You would really need a supercomputer to calculate the positions of the planets over time. Along came Nicholas Copernicus, 1473 to 1543. He suggested that maybe all the planets were not going around the Earth. They were instead going around the Sun in a heliocentric model, helio meaning sun, and they were going around the Sun in relatively circular orbits. This was not very popular in his day because much of the prevailing belief was that everything went around the Earth. The Earth was the center of everything, and everything should go around the Earth. So to suggest that maybe the Earth wasn't that important, that maybe the solar system was going around the Sun, was not popular to the point where it could be life-threatening. So Copernicus didn't really suggest this until he knew he was in the last year of his life. He knew he was dying, and that's when he suggested that this new theory that maybe the planets were going around the Sun. He still found some discrepancy in these circular orbits, so he had to retain a few small epicycles even in his model to help explain the exact position of the planets. But here's his basic idea. If the planets are going around the Sun, the planets that are more interior than other planets will be moving faster than the exterior planets. So the closer you are to the Sun, the faster you're moving, and the faster you're moving around the Sun. So there's a possibility that, say, if Earth were trying to view an outer planet, the perspective of that outer planet against the backdrop of stars is going to change. For instance, here's a picture of the Sun. Imagine this picture of the Sun. And, well, think of it this way. There's a more higher resolution picture of the Sun. And I guess you're looking over here. Yeah. So let's say the Earth was coming around here. You got Mars in front of the Sun, and you've got the Earth overtaking Mars is coming around the Sun this way. And from the Earth's perspective, you're looking at Mars and you're looking at all the stars beyond Mars in the backdrop there. But as the Earth is moving faster than Mars, then the backdrop is going to move and shift to a different perspective. And so it looks like Mars is shifting with respect to the backdrop of stars, but it's really the Earth-Mars perspective that's shifting. And then as the Earth continues on its way around the Sun, then Mars will continue looping back in the way that it was going originally. So because of this overtaking and then looping back, it makes it look like Mars is doing a loop-to-loop in the sky. It's just a matter of them both moving around the Sun at different speeds. Well, a little bit after that, we had Tycho Brahe, 1546 to 1601, born 3 years after Copernicus died, was the best astronomer of his day. He made very accurate astronomical measurements over a period of 20 years without the aid of a telescope. Here's a picture of Tycho Brahe. He used a very large sextant, and he could record very accurately the positions of the planets, and he did so for 20 years, and these were the most accurate data on the planets for the next 300 years. So not only was he the best astronomer of his day, he was the best astronomer in terms of the planetary data for the next 300 years. This picture of Tycho Brahe, it's hard to notice, but he is wearing a fake nose. And the reason Tycho Brahe has a fake nose is because he had an argument with a classmate at the university. It was in math class, and they were arguing over some problem. Maybe Brahe was saying 2 plus 2 is 4, and the other guy was saying 2 plus 2 is 5. And they argue and argue and argue, and finally they decided the only way to solve this argument was to have a duel at dawn. So they went out the next day to try to solve the argument, and they had a duel, and they're dueling with swords, and the other guy lopped off Tycho Brahe's nose. So he lost his nose. Evidently the other guy was right. 2 + 2 is 5, I guess. Yeah, I don't know if that was the argument, but it was a mathematical problem. He lost, and so for the rest of his life he had to put a nose on. He had some putty that might have been made out of a mixture of lead and some other elements, which possibly could have been accounted for his later death. He might have poisoned himself by using lead and or mercury in this putty to affix his nose. He also had a pet moose. The pet moose would walk into his house, make itself at home, and it was pretty tame. The poor moose one day met its demise when it found its way upstairs. At the top of the stairs was a vat of beer, and the moose started drinking out of the beer and then tried to make its way back down the stairs, and unfortunately it was unsuccessful in making its way back down the stairs. So that was the demise of the moose. Tycho Brahe, you might say, kind of met his demise in a similar way. I'll let you research that. It's probably not proper for me to talk about how he met his death. But in the last year of his life, he took on an apprentice, Johannes Kepler, and that's where we want to go from here. Kepler was a mathematician. He was not an astronomer. He wanted to look at all this planetary data that Brahe had. And so he was always asking Brahe for the data. Can I look at the data? And Brahe said, no, the data's mine. You can't have it. And he would just give him a little bit of data to work on, but he wouldn't give him the full data. And so Brahe did this for this first year. And then, strangely enough, after 1 year, Brahe died, and Kepler got all the data. So Kepler pored over this data for the next 11 years, and the results were his 3 laws of planetary motion. Here are Kepler's 3 laws of planetary motion. First law, all planets move in elliptical orbits with the sun at one of the focal points. This was one of the flaws in Copernicus's plan, was he had all the planets going around the sun, fine, but he had them moving in circular orbits, and because of that, he had to still add small epicycles to them because that was not accurate enough. So Kepler, poring over all this data, found that the orbits truly were elliptical, slightly smooshed, if I can say that, circles, as opposed to being pure circles. They were elliptical with the sun at one of the focal points of the ellipse. He found that the radius vector drawn from the sun to a planet sweeps out equal areas in equal amounts of time. How could he figure this out? Well, he pored over this data for 11 years and found these relationships and found that the planets move faster when they're closer to the sun and slower when they're further away. And by poring over this data for 11 years, came up with this empirically. His third law, the square of the orbital period of any planet is proportional to this cube of the semi-major axis of the elliptical orbit. How he came up with this? Pored over the data for 11 years and basically found that the time it takes for a planet to go around the sun, that squared, is proportional to the distance of the planet from the sun cubed. That is his third law, and it's empirical. It's strictly him poring over data, find mathematical relationships that worked, and fit the data. He didn't know why. He didn't know how. They just fit the data. It's just an empirical study, brilliant study, and brilliant conclusion on the motion of the planets. Well, Newton took Kepler's laws to the next level. He proved that all three of these laws were indeed a consequence of his gravitational law and other physics concepts. So Newton used these laws to help support his ideas on physics, made him feel good that his ideas were on the right track, and so he actually proved why they were true. For instance, if we look at Kepler's first law, the orbits of planets are ellipses. We have the planet going around the sun in an ellipse with the sun at one focal point. Newton proved that really the two-body system is like an offset baton, and that the two bodies, the sun and the planet, are actually moving around a common center of mass. And so as they're rotating around a common center of mass, it appears like the planet is going around the sun in an elliptical orbit, but it's really, they both are moving around a center of mass. The center of mass actually is inside the sun. The sun is so massive that the center of mass between the sun and a planet is inside the sun. So the sun is actually just wobbling around like this while the planet is going around the sun, and the net effect is like the planet moving around in an elliptical orbit. Kepler's second law. The planet sweeps out equal orbital areas in equal amounts of time. This is an empirical law that Kepler found, but Newton proved it based on conservation of angular momentum. If a planet is closer to the sun, it moves faster, and if it's further away, it moves slower. And if we were to calculate the area of the slice of pie that it moves through, say in 1 month, we would find that that area was the same. Here's a quick proof. I'm not going to spend too much time on this. The angular momentum of a planet going around the sun is a constant. It's the mass times velocity times the radius at any particular point. So the velocity of a planet is equal to the angular momentum divided by the mass of the planet divided by its radius at any particular point. If I were to look at this area, this triangle here, which is has one side equal to the radius, the other side equal to its change in displacement, dr, which is the velocity times change in time. I would say that the area is 1/2 the base times the height, 1/2 r times dr, or 1/2 r times velocity times change in time. I could put the dt on the other side, and I would have that the area with respect to time, the change in area with respect to time, is equal to the angular momentum divided by 2 times the mass of the planet. Angular momentum is constant, mass of the planet is constant, so this means that the change in area per time is equal to a constant. And that's how Newton proved Kepler's second law. Angular momentum of a particle of mass m moving with velocity v at a distance r, say going around the sun, is mvr. It's a constant. So if we actually had a planet going around the sun in an elliptical orbit, sometimes it's going to be closer to the sun, sometimes it's going to be further away. Angular momentum would be constant, mass of the planet is the same, so the velocity, the linear velocity times the radius at any particular point will be a constant. The closer you are to the sun, the faster you're moving. Further away from the sun you are, the slower you're moving. Such that this relationship holds. We are actually closer to the sun on the closest approach on January 4th during the year, and that's when we are moving fastest around the sun. The reason why it's winter time is because of the tilt of the Earth away from the sun at that moment, getting less insolation in the winter time, which is why it's winter in January. Not because of our position in relation to the sun, because we're actually closer to the sun at that moment. Kepler's third law. The square of the orbital period of any planet is proportional to the cube of the semi-major axis of the elliptical orbit. Newton proved this by saying that the gravitational force between the planet and the sun is really responsible for what is close to being a centripetal force. So if I get rid of the planet here, and I realize if the planet is going almost in a circular orbit, that its velocity would be 2 pi r over the period of the orbit. Hence, putting that into this equation. And then with a little bit of algebra, we can rearrange this, and we get that the period of time for a planet going around the sun squared is equal to 4 pi squared over g times the mass of the sun times the radius of the planet's orbit cubed. What's in the parentheses here, 4 pi squared over g times the mass of the sun, is a constant. So we have the period of time for the planet squared in the orbit is proportional to the radius of the orbit cubed. What's in the parentheses is sometimes called the Kepler constant for the sun, as 2.97 times 10 to the minus 19 seconds squared per meter cubed. You don't need to memorize that. But this is Kepler's third law in mathematical form. And if we actually measure time in years, Earth years, so that it takes the Earth 1 year to go around the sun, so we would have 1 year squared for our period, and we measure the distance in astronomical units, which the Earth is 1 astronomical unit away from the sun, so this would be 1 cubed, then with those units, the Kepler constant is 1. So we would have 1 squared is equal to 1 times 1 cubed, 1 equals 1. If you use years for time, astronomical units for radius, then 1 equals 1, and it works out. Hence, if you knew how many years other planets took, Earth years, other planets took to go around the sun, you can calculate their distance from the sun in astronomical units using just t squared equals r cubed. For instance, Mars takes 2 Earth years, approximately 2 Earth years, to go around the sun. You can measure that by looking at Mars and figuring it out. 2 Earth years to go around the sun. If I took 2 and square it, I get 4. And then if I take the cube root of 4, I get 1.52, something like that. And that would be the distance of Mars from the sun, 1.52 astronomical units. So it gives me an idea of how far the planets are away from the sun. It's a great way to do it, and that's how we can calculate how far the planets are away from the sun using Kepler's third law. Let's try an example. Let's figure out the mass of the sun. Calculate the mass of the sun using the fact that the period of the Earth is 3.156 times 10 to the 7 seconds. That's a period of 1 year in terms of seconds. And its distance from the sun is 1.496 times 10 to the 11 meters. Using Kepler's third law, we can solve this for the mass of the sun. And we get mass of the sun is 4 pi squared over g, radius cubed over t squared in terms of seconds and meters. Put in our numbers, 4 pi squared over 6.67 times 10 minus 11. The radius of the Earth's orbit, 1.5 times 10 to the 11 meters. And the period of the Earth's orbit around the sun in seconds, pi times 10 to the 7 seconds. And we get the mass of the sun is approximately 2 times 10 to the 30 kilograms. Earth is 6 times 10 to the 24 kilograms, so the mass of the sun is nearly, it's just about 1/3 of a million times the mass of the Earth. How about that? So based on these simple relationships, these simple laws, we can calculate the mass of these orbs out in space. Mass of the Earth, mass of the planets, mass of the sun, based on these relationships. That concludes the first lecture in Chapter 13 on Newton's law of gravity and on Kepler's 3 laws of planetary